Yeah, so as you mentioned a moment ago, neutron stars, as it says, are usually way too hot for us to even see. And that when they cool down to obviously still extremely hot temperatures, so it shows us how we often think of things cooling down. If something has cooled down, we think, oh, I'll be okay to touch it now. Not necessarily, right? So we have this idea of like this dualistic idea of hot and cold, where in reality things can always be hotter or colder than whatever they are. When they cool down to something still extremely hot, we can finally see it. So the question is, why would you not be able to see it when it was too hot? What is it that's happening that causes it to not be able to be seen? Well, basically, when things get hotter, well, first of all, let's start. When things get hot, we know they glow. Now, generally speaking, they glow red, don't they? If you think about it, if you get heat up a bit of metal, in fact, I'll get a picture, metal glowing. I'll just put metal glowing red. So, yeah, here's a nice picture. So this, it's a bit big. This, probably a bit of iron. It's been put in a furnace for a while, and as you can see, it's very hot and it's glowing red. So it's emitting red light, or maybe even towards a sort of orangey yellow light. And red light is, in fact, you can see as you go towards this end, it's more yellow, whereas down here it's more towards red. And red is a lower frequency of light, or a longer wavelength. It has a lower energy than yellow and some of the other colours. So when something is hotter, as you can see, this at the end where my cursor is hotter than where this is. It will be, won't it? Right? Then it emits. When it's hotter, it emits a higher frequency of light. Yeah, and so perhaps what's happening in this neutron star when it's really hot is that the frequency of light that it's emitting is actually beyond the spectrum beyond the range that we can see. So, if maybe I want to take a EM spectrum graph. So this at the top is the electromagnetic spectrum, the EM spectrum. This little tiny slither, which is actually, it's not to scale, this slither should be even thinner than it actually is. That's the only bit that we can actually see, and it's expanded out over here on the bottom bit. So you can see that the red end is the longer wavelength, also shorter frequency, and the blue sort of violet-y stuff is the higher frequency. So and you can see that if you go even higher than that, then we come to ultraviolet or X-rays, gamma rays, and cosmic rays. Not quite sure what cosmic rays would be exactly, so I'm not totally sure how accurate this is, but anyway, it gets mostly the point. And things that are still quite warm but not emitting any visible light may be emitting, or probably are emitting, infrared. So this bit of metal over here will still be pretty hot, like you'll definitely burn yourself if you touch it, but it's not hot enough to emit visible light. It will be emitting infrared. The only query that I've got with that idea is if we look at this one on the right first. So this is a graph demonstration of something called black body radiation. Now, I think a while ago we might have looked at what do we mean by the concept of black. So let's imagine that this circle here is black. Well, as far as we're concerned, it is black. But in reality, it's not really black when we think about what black would actually mean. So what's the difference between black and dark grey, for example? Well, dark grey would mean it could be blacker, it could be more dark. And so for something to be black, it would mean that it can't be more dark. So the question is, can this be more dark than it actually is? Almost certainly it can. Especially because it's on a monitor and if there's probably emitting some light, and I know when I turn off my monitor is not black. So there's nothing in my monitor that can make the monitor darker than it actually is. So that's one thing. So there's kind of an illusion going on there. But on top of that, the idea of something being black would mean that it absorbs all light. And not only all light, but all electromagnetic radiation, if we're going to be more scientific. But let's start off with just light. It absorbs all light, so it doesn't reflect any light at all. So if you see somebody wearing a black shirt, it won't be black, because you'll be able to see there are folds in the shirt, and the only way you can see the folds is because the light is being reflected from it at different angles, and that's how you're able to see that their shirt is folded. If you can't see any folds, then you could argue that it is actually black, or at least you perceive it as actually black. But if you can see any folds or shaping within the object, then it is not actually black. Now there are some things out there that people have made, types of black called Vanta black, and this is a guy wearing a t-shirt which is coloured Vanta black. Let's see how good it is. If you have a look carefully, we can see no folds in that t-shirt, whereas if I took this picture of a man wearing a t-shirt, I can quite clearly see folds. So I can't really call the one on the right black, but I might be able to call the one on the left black, but only as far as my perception goes. If I got a very sensitive light meter, I could probably detect some light being reflected from this t-shirt too, so that's also not really black. So technically black emits no light whatsoever, even with the most precise measuring techniques. You couldn't detect any light being emitted. It is a perfect absorber. Now, if it's a perfect absorber, it actually is also a perfect emitter. So a truly black object, if it could exist, if you heated it up, when it emits light, emits light perfectly. Some objects, like, well, let's say white objects, aren't very good absorbers of light, but they're also not very good reflectors of light. Sorry, hang on. Say that, no, scratch that, sorry. They are very good reflectors of light. I said it wrong. They aren't very good absorbers, but they're also not very good emitters. So if you're carrying some chips home from the chip shop, you wrap it in white paper, and it's not so good at emitting the heat away, and so you don't lose so much heat, and then your chips are still warm when you get home, whereas if you wrapped it in black paper, it would lose a lot more heat. So it's also why wood burners are coloured in black, painted black, so as the heat is emitted from the fireplace and the room gets nice and warm. So black is a good absorber of heat, but what we often forget or don't realise is also a good emitter. So even when something is glowing, like a star is emitting, clearly, like our sun is brightly white or yellowish colour. It's not actually yellow, but we won't talk about that now. It looks yellow, but then we could actually say that even though it looks whatever colour it is, it's actually a black body because it's very good at emitting light. Okay, so we often refer to stars as black bodies, even though they're clearly not black. They're usually white, and it means that they're just very good at emitting light. So this graph is showing what black bodies would do at different temperatures. So you can see that at 3000 Kelvin, which is really hot, it emits these different wavelengths of light. You can see it emits light of around about 10,000 or 12,000 the most. It still emits light at 6,000, doesn't emit any light at 4,000 wavelengths. This is just a unit of measurement, like distance, and so on. And so you can see the peak of the weight of these graphs slides to the left for hotter temperatures. So the peak for 4,000 is up about here, for 5,000 is up here, and for 6,000 is up here. So 6,000 has the peak at about so 6,000 Kelvin has the peak around about here, as in it gives off the most light at that wavelength. And you can see that this is all visible. So so yes, you're going to have the highest peak at a shorter wavelength, which is a higher frequency, but they're also still going to emit light of the other wavelengths. So if we imagine our neutron star, if we imagine our neutron star, and we say that a neutron star is going to emit light, it's really, really, really hot, and so maybe the peak is going to be around about here. So let's pick a different color. We'll pick purple. No, orange. Orange doesn't know. Maybe, yeah, let's do this one then. So maybe it's like this or something, right? But I can't do this. Notice that the rest of them they don't cross over. So even though the peak is more to the left, all the other wavelengths are still being emitted, and also they're being emitted more if they're hotter. So the peak slides to the left, but also all wavelengths are emitted more for hotter temperatures. So this theory actually wouldn't explain the problem of that we're getting at. I can't quite draw it. I'll use the line tool. If I just do it over here, yeah, let's do it over here, and okay, make it a bit thicker. Oh, maybe not that thick. And I want to make it a curve. So we put the and we want to change that a little bit, but so we've got to make sure that it doesn't go over the rest of them, but that the peak is more to the left. So this would be kind of more what it would look like. And so even though we can't see this stuff over the light over here, it's still emitting a load of light within our visible spectrum. So this doesn't really quite explain why we can't see neutron stars when they're too hot, right? So there's definitely scope for explanation there, but the reason why I explain the theory that is kind of wrong is so as you can look out for that if you're researching and somebody says, oh, the reason why you can't see it is because the hotter objects emit low wavelengths of light and you can't detect all this stuff over here. That wouldn't explain the theory. That wouldn't explain the fact that we can't see it, because it was, even though it is emitting a maximum wavelength of around about here, it's still emitting loads of wavelengths that we can see. It should do anyway. So I just wanted to quickly talk about that.